Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Amran bin Muhammad Rizwan and Muhammad Arif bin Muhammad Asri, and this is our group study for MEKP 5033 regarding power quality and energy efficiency, and which is under IR Dr. Zul Hasrizan bin Buhari, and our topic is the integrated power quality audit of feeder F10. So applying the structure evaluation procedure to a real multifaceted grid modernization challenge. So everything we present today follows one consistent six phase framework, which is phase one. Phase one is regarding the problem identification, where we categorize the feeder issues from network data, and phase two is technical characterization, where we quantify each disturbance mathematically, harmonics, transient, reliability. And phase three is regarding we compile candidate solution, the mitigation of technology available for each issue. And phase four is regarding evaluation and selection using a weighted scoring matrix to pick the best package. And phase five is detailed engineering design, where we size and specify real hardware. And phase six is regarding of proof of concept, where simulation confirm the design achieve compliance. So this same six-step logic structures the rest of the presentation. So why does feeder F10 need this kind of audit? So the rising PV and power electronic uh, penetration is introducing nonlinear, which is the harmonic generating load onto the distribution feeders. So at the same time, the utility capacitor banks installed for voltage support that creates switching transient. So under the wrong condition, it actually amplify rather than the downstream bus. So feeders today serve a mix of PV, industrial variable speed drive, and residential loads, as each of them is very different sensitivity to disturbance, and most prior research treats harmonics, transient, and reliability as separate problem, and rarely going as far as the real hardware. So the gaps defined on four objectives to quantitatively characterize each disturbance against IEEE 519 and IEEE 1366 benchmark, and compile and score candidate mitigation technologies in one common evaluation matrix, as it delivers full engineering design with real device ratings and filter parameters, and finally validate the selected package to proof of concept simulation. So our case study is feeder F10 as a 13.8 kilowatt distribution feeder serving a new park instrumented with continuous power quality, as it monitors at the point of common coupling and at each major load branch. So as shown in table 1, the feeder has four key segments. The PV solar farm is a grid-tied inverter source that introduces interharmonics. So manufacturing plant load A runs 6 past variable speeds drive drive that generate 5th, 7th, 11th, and 13th order harmonic, and the residential area load B is sensitive to voltage sags and experiences nonsense tripping, and the adjective feeder contributes a switch uh, capacitor bank used for voltage support, and this mixed network is exactly the kind of multi-source, multi-load feeder for our framework, and it is designed to handle. And this is phase one of our framework problem identification, where we screen the monitoring data against IEEE 519 2014 and IEEE 1366 2012 as the feeder's complaint resolved into three technical distinct issues and summarized in Table 2. So first, harmonics. The syntax is total voltage harmonic distortion exceeding 5% limit at a point common coupling, and the root cause is the combination of PV inverters and VST front ends. And second, transients. As we can see, voltage spikes of 1.8 to 2.4 per unit on switching events and rooted in the capacitor bank interacting the network through resonant uh, magnification. And lastly, reliability. We observe moderate SAIDI and but unusually low KID, which points to a root cause of high frequency nuisance tripping rather than sustained outages. So this is three issues now defined. The rest of our technical work. This is phase 2 where we quantify each disturbance and each disturbance mathematically. For harmonics, we use the standard THD definitions. Voltage and current harmonic distortion expressed as a ratio of RMS content to 50 Hz fundamental. On the voltage side, our THDV is at 6%, which exceeded the 5% IEEE 1519 limit for buses at or below 69 kilowatt. And looking at table 3, the fifth order harmonic alone measures 4.1 individually, exceeding the 0.3% limit, and this is our domain compliance violation. On the current side, total demand distortion is 9.4 and exceeding the 8% limit for our ISC to IL ratio range. So these are not just number on the papers. They translate into real impacts, increased transformer core and I squared R core conductor losses, accelerated cable insulation aging, neutral conductor overheating from triple harmonics, and this stripping of positive lead relays and VST inputs. Still in phase 2, we now characterize the transient and reliability issues. For transients, capacitor bank energized produces an oscillatory rush, and the adjacent feeder we measure 1.8 to 2.4 per unit at 600 to 900 Hz, but the downstream at VST bus this amplifies to 3 2 to 3 per unit, because when the high voltage and low voltage resonant frequency nearly match, the transient is magnified instead of them. The amplified peaks sits above the VSD DC bus trip threshold of 1.2 to 1.35 per unit, which is exactly why drive are tripping on switching events from a feeder that are not even directly connected to. For reliability, SAIFI and KID are related by definition. So our data shows SAIDIs of 9.2 minutes per year, only moderate, but SAIFI about 10.8 events per year, roughly 10 times uh, the 1 to 1.5 year benchmark. Since SAIDI is moderate, so SAIFI is very high. So KID works to just 8.5 plain terms. The it is frequent short duration nuisance tripping. So that completes our characterization. Phase 3 is about compiling candidate solution. Before we score anything, we first lay out the technology options for each issue category shown in table 4 to 6. For harmonics, the candidates are active harmonic filters that injects opposing current in real time. Passive tune filters offer low impedance shunt path K factor transformer directed for harmonic heating and 12 or 18 pass VST front ends that phase shift to cancel low harmonics. So for transient, we consider such protective devices that clamp over voltage, line reactance that limit DI or DT, and point on wave switching that closes at voltage zero crossing. For grid stability, we look at the D StatComs, dynamic voltage registers, and static transfer switches, and all of these move forward into formal scoring. Now this is phase 4 evaluation and selection. Every candidate was scored from 1 to 5 across 3 criteria: technical effectiveness, system impact, and reliability. And lastly is cost and feasibility as shown in the table II table 7. The highest scoring candidates were point on wave switching at 13 and a three-way tie at 12 between active harmonic filter, line reactance, and SPD or TVSS. Based on this result, our selected package has 3 parts. At the industrial plant, AC line reactors at each VSD input plus centralized active harmonic filter at plant PCC at the utility and feeder level, synchronous point-on-wave switching on the capacitor bank plus surge protective devices at the F10 PCC and at the PV solar IEEE 1519 compliant inverter. So the current control with dynamic reactive power management, and one more decision was worth nothing. We retained the StatCom at the PCC, and the energy park expansion, but isn't required for the present day compliance. Now into phase 5, which is detailed engineering design, where we turn the selected package into size, specified hardware, starting with the harmonic field, active harmonic filter. It is sized from manufacturing plant, which is 600 kilo kVA and 415 switchboard demand, and the measured 9.4% TDD. The plant load current is 834.7 amperes, and the harmonic current we need to cancel is 7.78.5, adding the 20% design margin, and at AHA rated current of 100 amps, which corresponds to the 75 kVA converter as shown in control loop architecture in figure 1. We also specify the K factor transformer. From the measured spectrum, we compute K equals to approximately 1.49, but for the design margin under partial load commissioning distortion, we specify K13 rated unit. As a documented alternative, we evaluated a single tune 200 kW passive filter but retained it only as a fallback. Its fixed tuning resists the resonant drift as the PV and the VST loading varies, whereas the AHA adapts in closed loop. Continuing the engineering design for line reactor sizing, a 3% reactor works out to approximately 229 microhenry per VST input rated at 100 amps at 415 volt, limiting the inrush DI/DT ahead of each drive diode front end. Shown also the 12 pass front end topology in figure 2. For the capacitor bank, mega VAR on the 13.8 kilowatt bus with 550 MVA shock current capacity. We specify point on wave switching with synchronous closing within half a millisecond of the voltage zero crossing. So the impact is dramatic. Uncontrolled closing of that produces 1255 amps, about 10 per unit of rated bank current, while the point on wave control closing brings down to 196 amps, about 1.56 per unit, and at 84% reduction. So critically that control result stays safely below the 1.2 to 1.35 per unit PST threshold value, which is what actually stops the nuisance tripping. Rounding out phase 5 for protection, we specify a space station class metal oxide surge arrested at the medium voltage F10 PCC and MCOV above the 13.8 kilowatt nominal 10 kiloampere discharge rating, placed as close as practicable to the protected bus. At the low voltage plant panel, we specify a Type 2 SPD rated at 20 kiloampere with a protective level under the 1.5 kiloampere per standard. So as C62.41.2, at the PV farm, we specify the IEEE 519 compliant inverter current control with dynamic VAR management and indicative 7.4 megawatt the STATCOM sizing for future expansion. So table VII on this slide summarize the complete final device specification. Every component we have walked through, from the AHF and KF13 transformer to the 12 bus front end line reactors, point on wave switch, both SPD levels, PV inverter control, and the future the STATCOM all in one place. This is phase 6, which is the last phase, proof of concept validation, confirming through simulation and that our design actually works. So figure 3 shows the harmonic spectrum. Figure 4 is the switching transient waveform, and the figure 5 the single line diagram of the complete system. So the result speaks for themselves. As we can see, current total demand distortion drops from 9.4 to 1.5%, comfortably within the 8% IEEE 519 limit. Capacitor switching also over voltage also drops from 2.35 per unit to 1.35 per unit, below the VSD 3 threshold. So to conclude, this audit carried a formal PQ problem evaluation procedure all the way from raw monitoring data through a size specified engineering designs, as this confirms both IEEE 519 and reliability compliant for the feeder F10 with a framework that is readily extended to the other renewable integrated feeders. So now we move on the references. So this slide lists 15 references that we have used. uh, regarding the methodology standard compliance, including the IEEE 519, IEEE 1366, and the NC/IEEE Transformer and Surge Protection Standard. So this is available for anyone who like to follow up on the technical background. That's all for our presentation. Thank you for your attention.